if they're oxidation processes or reduction processes. In the last section, we just wrote the half reactions down, looked at how the electrons must be moving around, and from that figure out if it's oxidation or if it's reduction. Now we're going to continue along the same lines and basically deduce the same information but with the full-on ionic reaction written down. So let's go and do that. Let's write an example down and we'll see if we can figure out what's going on. What if we have 2 iron ions, aqueous solution, plus 10 an aqueous solution, all right? And that yields 2 irons in aqueous solution. These have a charge of plus 2, plus 10, and these guys have a charge of plus 4. So notice that this is not a half reaction. This is a full-blown reaction, but it's an ionic reaction because it's a reaction in aqueous solution, and all we see are the things that are changing here. As I've said many, many times before, I want to make sure you understand, you don't go to the lab supply warehouse and buy iron 3 ions in aqueous solution, typically. You don't go buy 10 ions with a charge of plus 2 in a bottle. You don't do that. When you see equations like this that have charges all over everything, those are what we already call net ionic equations. We've learned about those before. Basically, you might have some iron sulfate or something like that, and you might have some tin nitrate or something like that, and those are bound up, and those are what's on your shelf stable on your shelf. When you put them in water, they react, and then the other part of these compounds, like the nitrate or the sulfate or whatever it was that you got grabbed off the shelf, those are just the spectator ions that are sitting around in solution but not doing anything. So when we see a reaction like this, 2 iron ions and then 10 ions and then iron ions with a different charge and 10 ions with a different charge, what we're showing here is this is what's really actually participating in the electron transfer, in other words, what's actually happening in terms of chemistry. There are other things potentially floating around solution. You might have nitrates or sulfates or other things that were originally bound to these species up there, but they're not participating, they're spectator ions. And we've talked about that stuff in the net ionic part of the course earlier, so make sure you understand that. So you're going to very commonly see these net ionic equations with charges all over everything because they're occurring in aqueous solution. All right. So the question is, the first thing I want to do is split this up into half reactions. That's what the purpose of this problem is. I want to split it up into half reactions, and I want to identify which half reaction is the oxidation process and which half reaction is the reduction process. And so what I'm going to do to pull that off is start looking around. Okay, one half of this reaction is dealing with iron. Iron is changing charges. The other half of this reaction is dealing with the tin because it's changing charges. So that's our big clue. So we write down 2 irons. Of course, the charge is plus 3. All right. And then something needs to happen to make it into a charge of plus 2. The only way a charge of plus 3 can go to a charge of plus 2 is if we add an electron to it. And what we're going to get on the other side is 2 irons with a charge of plus 2. But notice, this isn't quite right. We're not just adding 1 electron here. I actually have 2 iron ions. If I only add 1 electron here, then it's going to take care of one of the irons I have, but the other one is not going to be affected because I have actually 2 iron ions. So really, this half reaction has a 2 here. So you need to kind of use your logic. What you see is the before and the after. 2 iron ions, 2 iron ions. Okay, each one of these is taking plus 1 charge from an electron in order to do what it's trying to do here. But since I start with 2 and I end with 2, it must require 2 electrons to do that. So it's up to you to provide that when you're writing these half reactions. So that's why we put the 2 in there. All right, and so what we do is we go down below and we will try, let me go ahead and put another line here. Let's see if we can write the other half of this reaction. So here we have 10, 2 plus aqueous solution, whoops, AQ aqueous solution, and that gives me yielding 10, 4 plus aqueous solution. So here's before and after. I have an ion with plus 2 and an ion with plus 4. How do I change from an ion with a positive charge to an ion with an even more positive charge? The only way that can happen is if I liberate some electrons and get rid of some electrons from this guy, and then I have something that's even more positive. but how many electrons do I need to liberate? I have positive charge of 2, and then I end up with positive 4. So I have to liberate 2 electrons there, otherwise this is not going to occur. So when you're writing your half reactions, you're looking and trying to place where are the electrons going or coming, but also how many do you think are actually required? In this case, it takes 2 of them. All right? So the next question is, what is the this reaction above? These are the half reactions, okay? This represents one half of what's going on. This represents the other half. You can see that this iron ion is accepting 2 electrons. It's taking in 2 electrons. And when you gain electrons here, that is a reduction process. So I'm going to write down here, this is a reduction process. All right? Now let's look at the next part. This guy, okay, this 10, is actually liberating electrons because after the reaction, electrons are floating off, so to speak. So it's losing electrons, and we've said many times that when you lose electrons, it's an oxidation process. So if you have a test, you might be given a reaction like this, and you might say, hey, write the half reactions. Tell me which half reaction is the oxidation half reaction and which reaction or half reaction is the reduction process. So now you know enough to go figure out, okay, this is gaining electrons, so it's reduction. This is losing electrons, so it's oxidation. Now what if I ask you, what on the board here is the oxidizing agent, and what on the board here is the reducing agent, okay? So what we're trying to do is pick from what's on the left-hand side of the yield, which one of these is the oxidizing agent and which one of these is the reducing agent. And it's very easy here because now that I know this is a reduction process, I'm going to put a little semicolon, and I'm going to say Fe3 plus is, since it says reduction process, I'm going to call this the oxidizing agent. You just pick the opposite term, right? And since this is an oxidation process, then the 10 with the positive 2 charge is the reducing agent. And what is the reducing agent? It's actually the 10 2 plus. Okay? So whenever you're talking about is it oxidation or is it reduction, you're mostly just saying in this process what's happening. Is something gaining or something losing electrons? Fine. Okay? Then when you're talking about what is the oxidizing agent, what is the reducing agent, you're actually trying to pick something on the left-hand side of the yield arrow. One of these is going to be an oxidizing agent, one of them is going to be a reducing agent. In this case, this iron is the oxidizing agent because the oxidizing agent accepts the incoming electrons. And this is accepting the incoming electrons. And likewise, this 10 is donating electrons, so it's the reducing agent. The reducing agent is donating the electrons. Keep coming back to these definitions over and over and over again because they're so very important. All right, our final problem, just to kind of get more practice with this, what if I have zinc, which is a solid, plus 2 hydrogen ions, each charged plus 1, and I end up with zinc with a charge of positive 2 in aqueous solution plus hydrogen H2 gas, like this. All right, so this is, again, a net ionic equation because we see the ions present in here. And so presumably this H plus, prior to canceling the spectator ions, might have been tied up with something else. This zinc ion here might have been involved in something else. But what we're left when we see this net ionic equation is just the species that are actually participating. And what we can see here is that this zinc, okay, goes from a neutral atom into having a positive charge, and this hydrogen goes from having a positive charge into being a neutral gas. That's what's happening here. So if I want to write down the oxidation and reduction half reactions, let's just start with zinc first, okay? So what we're going to do is we're going to say zinc, okay, and on the other side of the equal sign, we're going to have zinc 2 plus aqueous solution. Now look at this and say, okay, this changes into this. How can that happen? This is a neutral atom, and then it becomes positive. So it has to liberate electrons in order to do that. How many electrons do you think it needs to liberate? Well, it needs to liberate 2 of them because I have a charge of positive 2. All right, so this is a half reaction. I'm going to skip a little space here and put a little line. And then I'm going to write in green the other half reaction. So what if I have 2H plus, And on the other side of the reaction, I have hydrogen gas. Now, how could this happen? I have two ions, each plus one, and somehow they become two atoms of hydrogen that are each neutral. The only way that you can do this is if this gains two electrons, because these two electrons are going to combine with these two ions, giving you two neutral hydrogen atoms. And anytime you have hydrogen, it's a diatomic, so it just always clumps together in terms of molecular hydrogen, in terms of a molecule. All right, but this is one of the half reactions. So the question then remains, which one of these is the oxidation process and which one of these is the reduction process? So let's go look at this. We have zinc changing into an ion and liberating, expelling some electrons. So it's losing electrons. So using our definition, this is an oxidation process. So let me just write it as oxidation process. All right. And then under here, if this is oxidation, you don't even really need to look at this in order to write that this is a reduction process. But if you wanted to check yourself, you'd look at this and say, well, this is accepting electrons. Accepting electrons, in other words, gaining electrons, is called a reduction. Now, if I also wanted to identify what species is the oxidizing agent and what species is the reducing agent, it's very simple now. Once I know that this is an oxidation process, this zinc on the left-hand side, zinc is the reducing agent. All right? And then, since this is a reduction process, this hydrogen ion I started with, H+, is the oxidizing agent. All right, so it's a little bit of a game of definitions, basically. You know, I mean, the main important thing is you want to know how to write these half reactions down and how to get the number of electrons in the right spot. Once you have them in the right spot, then you can claim, okay, this is losing electrons, it's an oxidation process. Since it's an oxidation process, zinc is also, by definition, a reducing agent because it's helping the reduction along by donating those electrons. This is a reduction process because it's gaining electrons. All right? It's also an oxidizing agent because it's the hydrogen is the guy accepting the electrons. So really, you know, these definitions, I understand this stuff really well, and they can still confuse me a little bit. So to be honest with you, what I do when I do these problems is I just write the half reaction down and I identify what is the oxidation process from losing electrons, and then I write down what is the reduction process by gaining electrons. So I write down oxidation process, reduction process. And then once you have this written down, you can flip to the other term and say zinc is a reducing agent, and this hydrogen ion is an oxidizing agent. To me, that's the easiest way, because the definitions, if you stare at them too long, can just end up confusing you for no good reason. Okay? So actually I'm going to do one more just to give you a little more practice with it. And that is, what if I have two irons, 3+ aqueous solution, plus 3 zincs, which is a solid, gives me 2 irons, which is a solid, plus 3 zincs, which is a charge of +2 in aqueous solution. So I want to do half reactions. Obviously, this is a net ionic already equation because I see my charges and I don't see much else besides ions and things. So here this iron is changing, it's changing charge, and this zinc is going from neutral to changing charge. The iron is going to changing charge over here. So if I want to write down the oxidation or the half reaction that's involving iron, I would say 2Fe3+. I've got to use my coefficients that I have. All right? And something's going to happen, and then I'm going to end up with 2 irons with a solid. Now, what's going to happen to the electrons? Here I have a +3 on each one of these irons, okay? And then I'm going to end up with a neutral iron atom. So let me ask you a question. If the 2's weren't here at all, if I covered them up, and if I'm going from +3 to neutral, how many electrons do you think it would take? Well, it would take 3 electrons to pile in here to make it neutral. It would take 3 electrons. But I don't have 1 iron ion. I have 2 of them. So instead of 3 of these electrons, it's actually going to take 6 electrons to do this. 3 of these electrons are going to combine and make one of these atoms, and the other 3 are going to go into there and make the other one. So you have to, when you're writing your half reactions, you have to look at the coefficients and really think about, with a real understanding of, okay, the electrons are leaving, and what charge are they? You got to figure that out and really get good at that so that you can put the right number here. Otherwise, you're just never going to get anywhere. All right, so that's one half reaction. Let me skip down a little bit and write down the other half reaction. So we did the one with iron, so let's go to zinc. 3 zincs, okay, and that's going to yield 3 zinc ions. Where do the electrons go? Here I have a neutral atom, and here I have an atom of zinc that has a charge of +2, or I should say an ion of zinc. If I cover up the coefficients like this, I go from having a neutral 0 charge on zinc to a +2. How many electrons does this zinc have to lose in order to give me a +2? Well, it'll have to lose 2 electrons in order to do this, right? 2 electrons. But I actually have 3 of these atoms doing this all at the same time. So it's 3 times 2 gives me 6 electrons that are actually lost. 6 electrons that are actually lost. So this zinc, each one of them is losing 2 electrons. Now I'm doing it 3 times over, so 2 times 3 is 6 electrons liberated. Notice, before I write anything on the board, in this process, or I should say in this process, I'm losing 6 electrons. But in this process, this guy is gaining 6 electrons. So it's kind of nice that one is losing 6 electrons and one is gaining 6 electrons. That has to be balanced like that in order for this reaction to actually work out. The number of electrons that you lose has to be equal to the number of electrons that is gained by something else. Okay, so that's just an important thing for you to remember. So which one of these is an oxidation process? And which one of these is a reduction process? Well, if we can go up here, you can see this is gaining electrons. And when things gain electrons, we call it a reduction process. So we call it reduction process. All right, and then we look down here and we say, okay, this zinc is actually losing all these electrons. And when we lose electrons, we've said it many times over, this is an oxidation process. Okay, so now we know which process is oxidation and which process is reduction. Now to find the oxidizing agent and the reducing agent is very easy. You've got to pick from what's on the left-hand side of the equal sign. This is iron with a charge of +3. So I say Fe3 plus is, and since this is a reduction process, you can automatically just write oxidizing agent. You just pick the opposite term. Since this is an oxidation process, you can write down that zinc is the reducing agent. And again, it's all consistent with the definitions. A reducing agent is something that donates the electrons. This is donating these 6 electrons. So that wraps the section up in half reactions and identifying oxidation or reduction processes in a half reaction. So just don't forget the big picture here. We're given these long reactions, which is sort of like what we've got up here, okay? And we split it up into half reactions so that it's a little bit easier to see what's going on with the electron transfer, but also the kind of undercurrent that I haven't really told you too much about, but I told you a little bit, is that when you split these half reactions out, you can see how many electrons are gained and how many electrons are lost, and they have to balance. That's going to be a crucial step later on when we balance more complicated equations. You're going to be asked to make sure and write these half reactions so that these guys balance the electrons gained and lost, and that's going to be a crucial step to balancing these chemical reactions. So I'm kind of easing you into it. You know, right now I'm talking about reactions, splitting them up, identifying oxidation and reduction so you kind of get a feel for it, but just keep in mind that that's the direction we're going. So stay with me. Make sure you understand these problems and follow me on to the next section where we're going to finally start to talk about oxidation numbers. And that's going to be a very important tool in helping us figure out also what's being oxidized and reduced in reactions, and as a nice segue or a nice lead-in to the real bread and butter of what we're trying to do, which is balance these redox reactions. Hello, and welcome to the section of the Chemistry Tutor. In this section, we're going to start to talk about the topic called oxidation numbers. Oxidation numbers, very important topic. It's going to help us learn how to track what's going on in a chemical reaction, which will lead us into being able to balance chemical reactions here in just a few sections. So up until now, we've talked about oxidation, we've talked about reduction, and we've talked about the definitions and what those things mean in terms of losing electrons and gaining electrons, and we've done a lot of work with that. And we've also talked about these things called half reactions, where you can take a big reaction and split it up into two smaller reactions that explicitly shows which electrons are being gained and which electrons are being lost, and that is a good way to help us figure out what is being oxidized and what is being reduced, because we can see those electrons being gained and lost in the half reactions. So we're kind of building our understanding up a little bit each time. Now we're going to talk about the concept of oxidation numbers. Now the big picture for what an oxidation number is useful for, big picture, is it basically lets us track electron transfer in a chemical reaction. And because it lets us track electron transfer, it basically is a way for us to tell what's being oxidized and what's being reduced in a reaction. So again, we've done a lot of this stuff before with the half reactions. We busted the reaction up into two pieces, looking at the electrons being gained and lost, and that tells us what's being oxidized and what's being reduced. The oxidation numbers is a way to get the same information. It lets us track the electron transfer, and it lets us figure out what's being oxidized and what's being reduced, but we don't have to write any half reactions on our paper. So we can have one big reaction written on a piece of paper. We can assign oxidation numbers to everything in that reaction, and just by looking at the numbers, we can figure out basically what's being oxidized and what's being reduced. So the big picture roadmap for this section is, I'm going to explain what an oxidation number is to you briefly, and then what we're going to do is write, there's a little bit of a process to find the oxidation number. It's not hard, but I need to write some rules down on the board. All right, and then once I get them on the board, then what we will do is turn our attention to just doing a lot of problems. We're assigning oxidation numbers to lots and lots of different elements and compounds. So an oxidation number is a number that you assign to the elements in a compound or to the elements in a polyatomic ion or some assemblage of atoms and elements like that. It's a number that you assign to those pieces there that basically represents the charge that's held by that piece. So if you have sodium chloride, there's two things in there. There's sodium and there's chlorine. So we can assign an oxidation number to sodium, and we can assign an oxidation number to chlorine. And it's basically representing the charge that's held onto by those two things that make up sodium chloride. And what we do is we assign those oxidation numbers to everything in the chemical reaction, and then by looking at the numbers, we can go and figure out basically what's being oxidized and what's being reduced. All right, that's basically what an oxidation number is. Now I want to stress something that's very important for you to understand before we actually learn how to assign oxidation numbers to everything in the reaction. And you'll probably read this in your book, and your teacher will probably mention it to you, so I want to say a couple of words about it. These oxidation numbers, in many cases, in many elements in the compounds that you're dealing with, represent the actual charge that we think that those particular atoms have in the compound. All right? So, you know, a lot of times, for instance, oxygen likes to have a -2 charge. So we'll say that its oxidation number is -2. But it's important for you to realize in the definition of oxidation number that it's really just a bookkeeping method. It's a bookkeeping method. So sometimes the oxidation number is going to be reflected in the actual charge, what we think this thing is actually charged to. But in some cases, depending on the compound you're looking at, the oxidation number that we give it isn't really going to line up with what we think that charge might be. So sometimes it's kind of a fictitious bookkeeping method. So what we're going to do is we're going to write down the method, and there's several steps that you're going to go through in priority order to put the oxidation number down on paper. And you follow those steps to the letter, and the number that you get for the oxidation number, just keep in mind that in most cases it represents the charge on that item, but it's fictitious bookkeeping in order for us to track the electron transfer in the reaction. So just keep that in mind, that in most cases it's a real charge, but sometimes it's fictitious, it's hypothetical, it's not really reflective of what's really going on in there. But what we care about in the end, in a little bit, is the change in the oxidation number. From one side of the arrow in the reaction to the other side, we're going to be looking at the changes in the number. So the change in the oxidation number is really what we're mostly caring about, not really the actual value of the oxidation number too much itself. So keep that in the back of your mind. So rather than continue to talk about this, let's go ahead and put something down that you can sink your teeth into and try to understand in terms of oxidation number. So let's take something simple. Let's look at something that I know you've seen. So sodium chloride, sodium and chlorine, okay? One atom of each, okay, ionic compound. What do you think, looking at the periodic table, what do you think the charges on these two guys would be? Well, if you look at chlorine, it is in the column right next to the noble gases. So chlorine always wants to have a charge of -1, if possible. All right? And sodium always wants to have a charge of +1, if possible. Okay? So these guys, +1 for sodium and -1 for chlorine, we call these oxidation numbers. So I told you a minute ago that it represents, in general, you can think of it as the charge on these guys. So this is the oxidation number. The oxidation number of chlorine would be -1. The oxidation number of sodium would be +1. Okay, let's look at another one real quick. Calcium chloride. All right, so again, chlorine almost always really wants to be a charge of -1. And so calcium here, always, if you look at the periodic table, it's in the second column from the left-hand side. It always wants to lose 2 electrons, so it always wants to have a charge of +2. So these would be the oxidation numbers. This is the oxidation number of calcium, it's +2. The oxidation number of chlorine is -1. Now notice a couple things that are important things for you to note is that in the sodium chloride compound here, we have +1 and -1, and we have subscripts of 1 there. So if you add up the oxidation numbers in that compound for all the atoms, 1 atom of sodium and 1 atom of chlorine, for the chloride, right? Then you have +1, -1, then the sum of those things is 0, okay? Now also look at calcium chloride. Here we have 2 chlorine atoms, so 2 times -1 would give us -2. If you add up all the oxidation numbers of all the chlorines, you're going to get -2. Calcium is +2, so +2 and -2 also give us 0. So what we're going to find out in a minute when I write all the rules of the oxidation numbers down is that's an important observation that's always true. In a neutral compound, like these are neutral compounds, right? The sum of the oxidation numbers of everything in there, when you take into account the subscripts and everything, has got to be 0. And that's something we learned kind of early on. We didn't call it oxidation numbers, but back when we learned how to put the charges up here and do the crisscross thing to get the subscripts, basically that's what that's doing. That process is ensuring that the compound that you end up with is going to have a 0 charge. All right, so these are oxidation numbers. Nothing too fancy, nothing too complicated. You might wonder, why are we even learning this? We already know how to do these. But what's going to happen is when you have more complicated compounds, how do you know what's going to take priority? Is the oxygen going to have -2? Is the hydrogen going to have +1? Sometimes when you just look at the periodic table at face value, you're going to get oxidation numbers that aren't right unless you follow the specific rules that we're going to lay out in a second. So for these simple 2-element compounds like this that are real simple, that are things we do a lot, it's pretty much going to be the charge that you read right off the periodic table just because it's that way. But there's a priority pecking order to writing down these guys that we need to learn. One more thing I want to tell you before we actually show you what that deal is, and this is kind of an aside that I want to make sure and point out to you. Okay, for oxidation numbers, it's kind of a convention that you write it like this: -2, +3, -4, whatever. You put the sign and then you put the number. So it's +3, -4, -2, whatever. Okay, back from before when we did the charge, we typically like to write that as 2 plus, 3, -5 plus, whatever. So when you're talking about the physical charge on an object, typically you put the number and then the sign after, the number and the sign. Sometimes I've been consistent with that, sometimes I haven't, but that is really what you should strive for, and in your book it's probably going to have it written that way. So if you see a plus after, it's implying that that's the actual charge. Whenever you see a sign and then the number after, it's implying that it's talking about an oxidation number. Now, I'm trying to reiterate this a lot because it's a common question that people have. These oxidation numbers, in many, many cases, are going to end up being the actual charge that we've been using on the periodic table all this time. So in most cases, you're going to look at them and it's not going to matter because the charge on the thing and the oxidation number are basically going to be the same thing. But I'm going to work a couple problems here in a minute that I'm going to show you that the oxidation number that you can get isn't really going to be lining up with what we think it should be, because the oxidation number is basically a bookkeeping method. It's a set of rules that we use to assign oxidation numbers to things, and the only thing we really care about is who changes, who increases their oxidation number and who decreases their oxidation number. So that's what we're looking for in reactions, and that information can tell us what's being oxidized and what's being reduced. All right? So I don't want to get too far ahead of myself. What I want to do now is erase this little introduction off the board, and then I will write down the rules of finding the oxidation number. There's not too many rules. There's 6 rules. They're very easy to understand. Let me get them on the board with you step by step, and then we'll work a lot of problems and give you a lot of practical practice with finding these oxidation numbers. Hello and welcome to this section of the Chemistry Tutor. In the last section, what we did is just introduce the concept of an oxidation number. We said it's a bookkeeping method to track electron transfer in a reaction. We gave a couple of very simple problems just showing you how finding the charge on the items in a compound basically is what we're calling the oxidation number, and I was very careful to stress that in some cases it's not going to make a line up with what you think the answer should be, and that there's a method for finding these oxidation numbers. So what I'm going to do now is start with a clean board and write down the method. It's not very hard, but you do need to follow it in priority order. So what I'm going to do is write down all 6 little rules that you follow for finding the oxidation number. It's very important for you to realize that when you get done with it, there's going to be 6 rules. There'll be 1, 2, 3, 4, 5, and 6. So when you're finding your oxidation numbers, you're going to start at rule 1, and everything at the top of the list is going to overrule any rule underneath it. So the way you go through when you're looking at your compounds is when you start from rule 1 and you march down the list, and everything that you find that applies, you go ahead and do that. So if something is at the top of the list, it takes priority over something that's at the bottom of the list, because sometimes you might have conflicting ideas about what to do. So this is very easy once you get the hang of it. Okay, so the very first rule, rule number 1, is something we've actually talked about before, and so here we go. There's a part A and a part B, so let's call it 1A. For atoms in a neutral atom, molecule, etc., the total of all oxidation, I'm going to do oxid for oxidation, numbers, is 0. All right, I actually mentioned that to you a minute ago when we did sodium chloride. I said, hey, when you add these things up, the oxidation numbers, when you sum them up, is 0, and that's all that this is saying. So as an example, if you have the atom just sitting off by itself, the atom iron, Fe, what it's basically saying is that you know by definition, since it's sitting by itself, the sum of the oxidation numbers of everything in here, which is just one atom, has got to be equal 0. So since you know that the sum of the oxidation numbers have to be 0, then it tells you that if iron is sitting by itself, neutral atom, by itself, the oxidation number of this must be 0. All right? If you have hydrogen gas just sitting off by itself, floating in a balloon or something, you know that the sum of the oxidation numbers in this molecule here is 0, because it says for atoms in neutral atoms, molecules, etc., any kind of compound, anything, the total of all the oxidation numbers has to be 0. So that means that since the sum of these oxidation numbers are 0, it's basically implying, and since it's the same atom in there, it's basically implying that the oxidation number of this hydrogen is 0. All right, let's look at something like magnesium bromide, MgBr2. What it's saying is the sum of the oxidation numbers in this compound is 0. So if I find the oxidation number of the magnesium, and if I find the oxidation number of the bromine, then once I multiply by the subscripts and add everything together, I'm going to get 0. So all Rule 1A says is something that you already really kind of know from what we talked about before. the sum of all the oxidation numbers in a neutral atom or compound always has to be 0. All right, that's all that this is saying. And it's an important rule, and it's the very first rule on the list. Now, 1b is very similar. That's why they wrap it up in the same rule. In an ion, right, the sum of the oxidation numbers is equal to the charge on the ion. The best way to illustrate this is by example. It makes a lot of sense whenever you look at it. Let's say I have the ion PO4, and this ion has a charge of -3. Notice that when I write 3 negative like this, the sign of this guy is written after the number, so that means this is the charge on this whole ion, right? So this whole ion has a charge of -3 when you kind of sum it all together. And that means here that the sum, this little sigma here means sum, it means you add everything together. The sum of the oxidation numbers has got to be equal to -3. So if I find the oxidation number of this guy, and if I find the oxidation number of this oxygen here, and then if I multiply by the subscripts and add all the oxidation numbers of everything in here, it's going to equal -3, right? And it's the same kind of rule as what's going on here. The charge on these things are always 0. So the sum of the oxidation numbers really is equal to the charge here too. It's just always 0. So anytime you have a charged thing like an ion, the sum of the oxidation numbers is equal to that. What about NH4, the ammonium ion? All right. So again, the sum of the oxidation numbers in this case is going to equal +1, because the total charge of this whole ion is +1, so the sum of the oxidation numbers are going to be that. What about a chromium ion, a single atom that has a charge of +3, right? So that means the sum of the oxidation numbers is going to equal +3. So this is rule number 1. Very simple rule to understand based on what we've talked about before, but very important for you to understand. When we have neutral atoms, neutral molecules, the sum of the oxidation numbers of all the little oxidation numbers in there have got to add up to equal to 0. When we have charged objects like ions, the sum of those oxidation numbers have to add up to the total charge on that ion. All right? So that's rule number 1. And that basically applies to everything, because everything in nature is either going to be a neutral atom or molecule, in which case the oxidation numbers will sum to 0, or it's going to be an ion of some kind, in which case the oxidation numbers are going to sum to give you the charge on that ion. So everything's going to fall into one of those two categories, and that's why it's rule number 1. It applies to basically everything. It's top of the food chain, always going to apply. Now let's go and look at rule number 2. Okay, so going down the list. Here's where we start assigning oxidation number. In compounds, group 1A metals have oxidation numbers of +1. What this means is group 1A, that's the very first column in the periodic table, the one with hydrogen in it. All of those guys have oxidation number of +1. Notice this is what you would expect. When you look at the periodic table, I already told you how to read the charges, kind of like the charge that it's going to want to have. The very first column, the one that hydrogen is and all those things, they always want to be +1. So this is just affirming that. It's very high up the list. It's telling you that these things, these metals over there, they're extremely predictable. They all want to have a charge of +1, which means they all want to have an oxidation number of +1. Group 2A metals have oxidation numbers of +2. Okay, so that's the column that's right next to the first one. So the first column wants to have charge +1. Second column, the one right next door, wants to always have a charge of +2. And again, we've been using this fact over and over, but we're just kind of putting it on the board in a priority order, showing you this is very high up the food chain. These guys are extremely predictable, so they're going to be something that we're going to see all the time. So let's give an example. What if I have sodium SO4, okay, Na2SO4. What this is saying is when I look at this guy, I'm going in priority order, right, if I were to look at it. So what it's telling me is this is a neutral compound, Na2SO4. It's not an ion, so the sum of all these oxidation numbers is going to be equal to 0. That's the rule number 1. But then I come to rule 2 and I see that, the guy applies here because sodium is in group 1A. So what I can tell is that Na has oxidation number of +1. I know that right away because it's rule number 2. All right? What if I had something like calcium PO4? All right? Again, calcium's wrapped up in here. I don't have anything on this list about phosphorus or oxygen yet at all. But I know that calcium is on this list. It's in group 2A, so that means that calcium, the oxidation number, is +2. All right? So I haven't given you rules to find the other ones yet, but what I'm trying to tell you is that you follow a priority order. You look and you see first, okay, do I have any group 1A or 2A elements in this guy? And if I do, I know what those oxidation numbers are. And then I'm going to have a rule 3 and 4, and you just keep marching down the list until you've assigned a number to everything in whatever it is you're looking at. All right? Let's go to rule number 3. Rule number 3. In compounds, fluorine F oxidation number is -1. That's important enough that it goes off by itself. Fluorine is always going to have a -1. So for instance, if you have a compound HF, then fluorine, you know right away, is -1. All right, so again, we look at this guy, HF, we see the F here, and we see that it's right here, it's always -1, so we know right away without doing anything else that the oxidation number is -1 for that guy. All right, so let's look at step 4, or in rule number 4. In compounds, the element hydrogen has oxidation number is equal to +1. Okay, so if you think about that, that makes sense, because if you look at hydrogen on the periodic table, hydrogen is in that first column, and it usually does like to have a charge of +1, right? So let's give another example. HCl, hydrochloric acid, right? So we know without looking that the hydrogen in here, okay, has an oxidation number of +1. Okay, oxidation number of +1. Now again, I know you don't really see it yet until we work the problems, but you know this is a priority list. So for instance, we haven't talked at all about chlorine yet, so we don't know anything about what's going on with chlorine yet, but we know hydrogen is going to give us this. We have rules that talk about the group 1A metals and the group 2A metals like sodium and calcium and you know, things like that. And we have rules that talk about certain things like out of place, like why would fluorine be listed as a separate rule? That's because it's a little bit higher up the priority chain. Fluorine always wants to have, or almost always wants to have, a -1, so it's up there. So things that are lower on the list, you may not actually get to whenever you're doing your calculation of the oxidation number, because you may find the answer to all of the elements in there without having to get to the bottom of the list. So I guess it just needs to show you by a few problems what I'm talking about, but just keep in mind this is a priority list. The things at the top of the list are the kind of the surefire things. The thing at the bottom of the list, you may not even get to them because you know you may solve the problem before you get down there. So let's look at 5. Okay, in most compounds, oxygen has oxidation number -2. And again, this is something that you've seen before. Oxygen is over in that column toward the right by the noble gases, but it's 2 columns over, so it usually likes to have a -2. But again, this rule is down farther on the list. So even though it says in most compounds oxygen has an oxidation number of -2, depending on the compound you have, oxygen may not have an oxidation number of -2 if you get through all of these rules that are up above it, and it dictates that hydrogen is something a little bit different than -2. So you just go through the list in priority order, but don't get the idea that just because it says -2 here, oxygen is always going to have -2, or just because it says hydrogen is +1, that it's always going to be +1. Though that's not true. This is a priority list. So when you're going down there, if you calculate that hydrogen has an oxidation number different than this because of rules that are above this, then that's just going to be the answer. So this is a priority list. Just keep that in mind. Let me go ahead and show you an example here with the oxygen. Carbon monoxide. Oxygen is going to be equal to -2, an oxidation number. -2. Okay? All right, let me put one more thing, see if I can squeeze it in. 6. Okay? In 2-element compounds with metals, comma, group 7A, in 2-element compounds with metals, group 7A elements, those are the ones nearest the noble gases, they have oxidation number of -1. Okay. Group 6A metals have oxidation of -2, and group 5A guys have elements have oxidation number -3. So let me give you an example, okay? So, or a quick example. Group 7A, that's the column right near the noble gases. So those are things like fluorine, chlorine, bromine, ... All right. Group 6A, that's not the column right next to noble gas, but the one over just to the left. That's oxygen, silicon, oxygen, sulfur, ... Okay? And the group 5A would be things like nitrogen, phosphorus, arsenic, ... All right, so this basically outlines all of the rules needed to find oxidation numbers. I know it looks like a lot, you know, we throw them on the board, but basically this is it. And so what you do is if I give you a compound and I say find the oxidation numbers of everything in this compound, then what you would do is you would start with rule 1 and you would figure out, okay, is it neutral or is it not? And you would assign the rule here. And then you would go to rule number 2 and you would figure out, okay, do I have any group 1A metals or 2A metals? If so, I assign those oxidation numbers. And then you would say, okay, look down here and you would say, okay, do I have fluorine in there? If I do, I assign that a -1. Then you would say, okay, do I have any hydrogen? And then I would assign +1. Then you would say, okay, do I have any oxygen? And if I do, I would have -2. And then I would say, all right, do I have any group 7, 6, or 5 in these 2-element compounds? And then if so, I would assign -1, -2, -3. But what I'm trying to say is that as you do problems, you'll figure out that you might not get all the way to the end of this list. You might complete the problem up here in rule number 3 or 4 and have all the oxidation numbers for everything you need. So there's no point in talking about it anymore. We need to do some problems. But before we do that, I need to give you a couple of exceptions. Okay? With all rules of all kinds, there's always exceptions. All right? So let me give you a couple of exceptions because you're probably going to run into them and then you're going to scream and say, well, why didn't it follow these rules? Okay? So this is an exception to rule number 4. Rule number 4 is the one that talks about hydrogen, saying the oxidation number in compounds with hydrogen is positive 1. Okay? If hydrogen is bonded to a metal, okay, to a metal, then the hydrogen oxidation number is actually negative 1. So notice what this rule said. It said in compounds, hydrogen's oxidation number is positive 1. So you would take that to the bank and you would assign positive 1. However, there's an exception. If hydrogen is bonded to a metal, okay, then the oxidation number is negative 1. Now, what could that be? Let's say you have some weird thing, some weird looking thing like NaH, which, believe it or not, is possible, or CaH2, calcium hydride or something like that. All right? So in both of these cases, you have the hydrogen bonded to a metal. All right? So the hydrogen oxidation number is negative 1. All right? That's an exception because that's kind of rare. You don't see that too much. When you see hydrogen in compounds, it's not bonded to a metal most of the time. Think about it. Water is H2O. That's bonded to a nonmetal, right? Hydrogen is bonded to a nonmetal. What about hydrogen sulfide? That's a nonmetal. What about hydrochloric acid, HCl, right? So most of the time, hydrogen's bonded to things on the right-hand side of the periodic table, and in all those cases, the oxidation number of that hydrogen is going to be positive 1. But in the crazy cases when you have metal hydrides, where you have like a sodium hydride or calcium hydride or something like that, that's weird when it's bonded to a metal. In that case, the oxidation number of hydrogen is negative 1. So we put it as a footnote because it's not very common, but you need to know about it. Okay? Only one more exception, then we're done. Exception to rule number 5. Which rule number 5 is dealing with most compounds. Oxygen has oxidation number negative 2. Okay? When oxygen atoms are bonded to one another, okay, then things are a little bit different. So for instance, you have this thing called peroxides. Let me just go ahead and put it like this. Peroxides. You've heard of hydrogen peroxide, right? So peroxide. For instance, H2O2. This is hydrogen peroxide you find in your medicine cabinet. Right? In this case, the oxidation number of oxygen is equal to negative 1. So if you follow the rule blindly, it says most compounds, oxygen has an oxidation number of negative 2. But we're giving you an exception to that. We're saying, okay, when oxygen atoms are bonded to themselves, so here you have H2O2, you have 2 oxygen atoms, attached inside of another compound. In that case, the oxidation number is going to end up being positive 1. All right, so here we have all of the rules needed to figure out the oxidation number of elements and atoms in a compound or an ion. So what we're going to do in the next section is we're going to use these rules in priority order to go and figure out the oxidation number. And don't forget the big picture. Why do we go through all this trouble? The reason is because when I have a chemical reaction laid out, I want to be able to assign an oxidation number to every single atom in every single compound in that reaction. And once you get the hang of it, it's very fast. It takes you just a few seconds. And then I'm going to look at the changes in the oxidation numbers on the left-hand and on the right-hand side of the arrow in the equation. I'm going to figure out what is increasing their oxidation number and what is decreasing their oxidation number. And that's going to tell me what's being oxidized and what's being reduced. And that's why we're doing this. We're trying to track electron transfer to figure out what's being oxidized and what's being reduced. So again, real rapidly, rule number 1 says that if you have a neutral compound, the sum of the oxidation numbers of everything there has got to be 0. If you have a charged ion, the sum of the oxidation numbers is going to be equal to the charge. Rule number 2 is if I have a column 1A or column 2A metal, then the oxidation number is +1, +2. That's very high up on the list. Fluorine is always going to have an oxidation number of -1. Hydrogen is always going to have an oxidation number of +1 unless it's actually bonded to a metal, in which case it'll have a -1. Okay? And then we have oxygen. Oxygen is going to have an oxidation number of -2 unless oxygen is bonded to itself like in a peroxide, and then the oxidation number is -1. And then finally, in two-element compounds with metals, the things on the right-hand side of the periodic table, column 7, 6, and 5, are going to behave like you would expect. The column 7 guys are going to have charge -1. The column 6 guys are going to have charge -2. The column 5 guys are going to have charge -3. That's what we actually learned a long time ago. But notice that this is at the very bottom of the list. So as I work problems, you'll see that sometimes the answers you get for some of these are not quite what we expect, because this is a priority list. If I get all the oxidation numbers after I get to this step, then nothing below it even matters. And so that's something you have to keep in mind. So let's go and wrap this section up. Go on, follow me to the next section, where we'll finally put some compounds down and give you some real practice with finding these oxidation numbers in compounds and ions. Hello, and welcome to this section of the Chemistry Tutor. We've done a lot of groundwork here in the last couple of sections talking about what an oxidation number is and the rules for finding oxidation numbers. But really, until you get to this section right here that we're in, so that you can actually apply all of these rules, you really can't really get a great appreciation for how to do it. So we just need to dive in and work a lot of problems, and that's exactly what we're going to do. It's very important to be able to know how to do these oxidation numbers right, so that you can actually use it for your chemical reactions and figuring out what's being oxidized and reduced later on. If you don't have a good grounding in this, then follow-on topics are going to be tough, even when they're not hard. So what I've done is I've left all the rules on the board. Everything is still here. I haven't really erased anything. Everything's still here. And what I'm going to do is work on the right-hand side for all the problems, so that what we can do is refer back to the rules that we've already used. So you don't need to write anything down as far as rules. I've got them all on the board. And they're in your books. You might want to jot them down at some point, but as far as working these problems, I've already got them on the board. So let's jump in. I think you'll be surprised at how some of this stuff ends up working out. So let's do problem number 1. We have a potassium ClO4. Okay, so this is a compound. We've got potassium atoms in there, we've got chlorine atoms in there, and we've got oxygen atoms in there. And so, if you just look at it, if you look at the periodic table, you're going to say to yourself, okay, well, potassium likes to have charge of +1, chlorine likes to have a charge of -1, and oxygen likes to have a charge of -2. That's what we would typically say from everything we've learned up until this point. Some of those answers are going to be right, but one of them is not going to be right. So if you just go from your gut instinct, what you think should be, you're going to be wrong a lot of times. You have to use the method that we've outlined here. So the very first thing we do is we go and we look at the priority order. Rule number 1 says for atoms in neutral molecules or whatever, the sum of the oxidation numbers has to be 0. And rule number 1 applies here. In fact, rule number 1 is always going to apply because we're almost always going to have neutral atoms here. So the way that I want to put this down is I want to put an asterisk here, just to kind of remind myself. What I'm going to say is that the sum of the oxidation numbers is going to be equal to 0. And in parentheses, I'm going to put rule 1. This is not something you have to do, but what I'm going to do is write down what I'm doing, and I'm going to put the rule that I'm using, so that if you're on a test and the teacher sees that you know what rules you're using, then you can get some partial credit if you don't get the final answer correct. All right, so I like to do that. Plus, it also reminds me of what I'm doing. So I've done rule number 1, okay, and then I go down and look for rule number 2, and I see, does rule number 2 apply? Well, it says in compounds group 1A metals have oxidation number +1. What we have here is this guy, and this guy is in column number 1, so it is a group 1A metal. All right, so I'm going to put an asterisk here, and I'm going to say that for potassium, K, the oxidation number is +1. All right, and I'm going to write down to myself rule number 2, okay, because rule number 2 applies. All right, now the next thing you have to do is look and say, okay, do I have enough information to find all the other oxidation numbers? Well, I know the oxidation number here, and I know they all sum up to give me 0, but I don't know what chlorine is and I don't know what oxygen is, so I don't have quite enough to do the final answer. So I go down and I say, do I have any group 2A metals, right? I don't have anything like that in there, so I skip over that. Let me go to step number 3, or rule number 3. Do I have any fluorine in here? And I go over here and look and I say, I don't have any fluorine in there, so that's not a big deal. Then I go and look at number 4. Do I have any hydrogen in here? I go over here and I don't see any hydrogen, so that doesn't apply. I go down to number 5. Do I have any oxygen in here? And oxygen would be a -2. I do have oxygen in here, so I put a little asterisk and then I say the oxygen is -2, and that's rule 5. All right? So then I go back and look and see, do I have everything needed to find everything here? I know what potassium is because that was given in the rules here. I know what oxygen is. I don't know what chlorine is. So I think, okay, a lot of students will think, okay, well, I'm going to go and keep looking. So I'm going to go keep looking down here and down here. Eventually, I'm going to get down to the group 7A nonmetals, and I'm going to see that they have oxidation number -1. So I might be tempted to put for chlorine -1 here and say, okay, I've got all the oxidation numbers, but you would be wrong, okay, if you do that. Because, believe it or not, even without going to the bottom of this list, I actually have enough information here to find the answer. And the reason is because I know what potassium is, I know what oxygen is, and I know that the sum of all of these oxidation numbers in this compound have got to be equal to 0. That is critical, crucial information. So let me see if we can use this. What is the oxidation number of potassium here? We just said it was +1, so I'm going to say, okay, 1. What is the oxidation number of chlorine? I don't know what it is, so I'm going to add to it, I'm just going to put Cl there because I don't know what that oxidation number is. What is the oxidation number of oxygen? Well, it's -2, but I have 4 atoms here, so I have to say 4 atoms times -2 for each one. And all this stuff has to be equal to 0. What I am doing here is I'm applying rule number 1, which is the very first rule in all of these things. All right? So I found rule number 1. I had to use this rule. I had to use this rule. But when I get down to this point, I can write like a little tiny equation there, and I can figure out what chlorine is because the sum of these guys have to be equal to 0. So what I do is I say 1 plus Cl. 4 times -2 gives me -8 is equal to 0. And then I have Cl minus 7 is equal to 0 because -8 plus 1 gives me -7. And if I move the 7 to the other side, then chlorine is +7. So what I have found is the oxidation number of chlorine is actually +7. So the way that you write this down for your answer, or you can do it any way you want, you can circle them, I guess, but a lot of the ways that you'll see it is you'll see the compound rewritten, KClO4. And the way I like to do it is I like to draw a line from the potassium, and you just put +1 up here. Put the line from the chlorine up here, and you put +7 up here. And you put the line from the oxygen, and you say -2. So when you have lines drawn like this,